Welcome back, everyone. So in the previous video, we introduced this concept of isotopes with regards to elements. Isotopes are elements, they have the same number of protons, so they are the same element, but they have different atomic masses, so that means they have different numbers of neutrons. As like a practical example, maybe a good summer example as well. I'd like to think of isotopes as 3 different brands of strawberry ice cream. Let's say I have 3 different brands of strawberry ice cream. They're all strawberry ice cream, but maybe one brand of strawberry ice cream has more strawberries in it than another brand. Here's an example, maybe a more chemical example of neon to illustrate the concept of isotopes. Let's say I was to take a sample of neon gas from this neon light. And if I was to analyze it, I would see that it's all neon gas. All of those atoms have the same number of protons, but some of them have a mass of 20. Much smaller proportion have a mass of 22, and a really tiny proportion has a mass of 21. So we would say that neon has 3 isotopes. Depending on the element, some elements have more isotopes than others. That's all well and good, you say, but how does that pertain to the periodic table? Well, when you look at the periodic table, for example, neon, if you were to look at neon, I just got done explaining and showing you in this cartoon that neon has 3 main isotopes. When you look at the periodic table for neon, do you see 3 atomic masses that are published? You don't. You only see 1 atomic mass. If you're looking at the periodic table that I have given you in this module, you see that neon has an atomic mass of 20.18. There's only one atomic mass there. How did that come into play? How did we get that number? So that number, that average atomic mass, comes into play by taking a weighted average of the abundances of the masses and the abundances of the isotopes. What that means is that to find the average atomic mass for an element, what's published on the periodic table, you have to take a weighted average. I cannot just add up the 3 masses of my isotopes if I've got 3 and divide by 3, because that does not take into account the fact that I have more of one isotope than another. I have to take what's called a weighted average. And so what that means mathematically is that the average atomic mass, what's in your periodic table, is calculated by taking the sum, this little symbol here that just means sum, by taking the sum of each isotope mass in AMU, and I multiply it by its corresponding percent abundance, but that percent abundance has to be in decimal form. So if I give you a percent abundance, like I did in the previous example, if I give you a percent abundance in percent, you need to take it and divide by 100. So let's do an example. Let's say I have 2 isotopes, 2 flavors of chlorine. One has an atomic mass of 35. One has an atomic mass of 37, and I have these 2% abundances. If I was to find the average atomic mass for chlorine, calculate that, I need to multiply the corresponding mass and percent abundance in decimal form and add them up. So since chlorine has 2 isotopes, when I calculate, here I gave you the specific atomic masses for those 2 isotopes. If I hadn't given you if I hadn't given you those, then you should use this. But since I gave you the specific atomic mass for each isotope, you should use that in your calculation. Apologize. So the average atomic mass for this sample of chlorine is going to be equal to, my first isotope, the mass of my first isotope, multiplied by its abundance, divided by 100, because it has to be in decimal form. Add that to my second term, my second isotope. So I'm going to add that to the product of my my second mass multiplied by my second abundance in decimal form. When I do those multiplications and add them together, I get an average atomic mass of chlorine of 35.46, which is actually pretty darn close, atomic mass units, which is pretty darn close to what is actually written on the periodic table. So for these problems, I'm not going to be super picky about significant figures. Like I said, if I give you an atomic mass with more decimals, then you should use it. Take-home message is that the average atomic mass for an element, what's on the periodic table, is a weighted average. It takes into account the mass of each isotope as well as its abundance in decimal form. And that means if I give you its abundance in percent, you need to take that percent and divide by 100. So there are 2 or 3 more examples similar to this on the Canvas worksheet. In the next video, we're going to talk about how to use this equation for average atomic mass to actually determine the atomic mass for a particular isotope for an element.